Hello and welcome to our Wednesday webinar from the International Centre for Sustainable Carbon. My name is Benedicta and I'm part of the communications team here. Our monthly webinars are based on our reports, which are available from our website, sustainable-carbon.org. Please type any questions in the questions box as we go along and we'll answer them at the end of the webinar. The subject for today's webinar is the role of biomass in production of cement and iron and steel, presented by Professor Jenny Jones. Over to you, Jenny.
Benedicti. Good afternoon, everyone. So I'm Jenny Jones. I'm now retired, actually, so a visiting professor at the University of Leeds. And yeah, as Benedicti said, this webinar is about a report myself and two colleagues have been preparing. Leilani Darvel and Bijal Gudka. And obviously there's a lot more detail in the report, so this webinar will just give you a flavour of the contents of that report. And if you're interested in more detail, I believe the report hopefully will be out in February around that time. So the presentation outline is shown on this slide. I'll start with an introduction to CO2 emissions from heavy industry and the necessary decarbonisation for our net zero trajectory. Before explaining the main process for cement manufacture and look at where biogenic fuels can come in to displace some of the current fossil fuels. Then I'll do something similar with iron and steel manufacturing, what the role of carbon is there and what the opportunities are for biogenic carbons. And I want to show just one slide on some of the carbon science that affects the substitution rates that can be achieved when you're trying to substitute coal and coke for biomass derived products. And then I'll summarize a little bit of the research development deployment for using biomass in iron and steel manufacturing, and then some concluding remarks and comments. So in 2021, the total global CO2 emissions were approximately 50 gigatons, and about 12% of those are from cement and iron and steel manufacturing, shown in this figure. So approximately 6 gigatons per year from those two sectors. Both those sectors are still heavily reliant on coal. For example, over a gigaton of coal and coke was used in iron and steel making in 2022. And coal is the traditional fuel used in cement production as well. We're seeing rapid urbanisation and development of some parts of the globe, which increases the demand for cement and iron and steel. And the net zero trajectory requires a decreased reliance on coal because of the high carbon intensity it brings to those manufacturing processes. Both sectors are challenging to abate. There's inherent CO2 emissions with cement manufacturing. There's multiple sources of CO2 emissions with both of those manufacturing processes. So they're a challenge to abate. And actually, steel and cement production in some parts of the world, like particularly China, is increasing rapidly and often uses high carbon intensity technologies. So if we have improvements in efficiencies of production in some of the more developed countries, these are being offset by the increase in production in parts of the world that have high carbon intensities. So this means neither sector is on track for its decarbonisation targets. And every geographic region is using a different mix of manufacturing approaches with different carbon intensities, and they have their own roadmaps for decarbonising. This slide shows the projections from the International Energy Agency for the 2050 share in production for the two sectors, for steel and for cement. And this is based on one of their scenarios that they've modelled. There's many CO2 reduction options for decarbonised in these sectors. Efficiency improvements is a big one, and reducing demand by improving the products, for example, reducing the iron content in steel content in some of the products. So demand reduction, circular economies and using waste streams is also attractive to bring down carbon dioxide emissions, and of course employing best available technologies. There's also interest in many of the roadmaps. There's also a push for electrification of processes and increasing renewables on the grid, so that the electricity use in these sectors, the CO2 emissions from those also decreases. And then, of course, we have technology switching and fuel switching, which is where biomass comes in, and we have carbon capture and storage. So if we look at the iron and steel one, at present, the blast furnace route for iron making dominates globally. I think it's responsible for about 70% of the global steel manufacturing. It's the most carbon intensive. Many parts of the world have young fleets of blast furnaces, including Asia Pacific, which are producing, a large share of the world's iron and steel. So substantial decarbonisation of blast furnaces is still relevant. And this top figure shows projections for where the reductions in carbon might come from the manufacturing process. And to put this into context, in 2021, the fuel mix in iron and steel globally was 74% coal and 8% natural gas. So you can see the transition in just the next 30 years, or less than 30 years, is to more scrap-based secondary processes. So that's the electric arc furnace. So as the blast furnace fleet reaches end of life, it's replaced with these other technologies. Hydrogen features strongly in the roadmaps, and bringing hydrogen in as a reductant and fuel. And then we've got carbon capture and storage, and then we've got bioenergy with carbon capture, utilisation of storage as well. There'll still be a role for fossil fuels by 2050 because of its importance as a reductant and as a fuel in the blast furnace fleet. Similarly for cement, I've got numbers for 2020. Unabated fossil fuel use was 92% in cement production in 2020. So by 2050, still going to be fossil fuel use, but now with carbon capture, utilisation and storage. And then these two blocks in the middle at both 19%, we've got bioenergy with carbon capture, utilisation and storage, and bioenergy without that. We've got some unabated fossil fuels use, a role for hydrogen, and then electrification as well. So it's a big challenge to get there, and there is a role for biomass. It's not a major role, as you'll see, although it will give significant carbon reductions where it's implemented. For cement manufacturing, it has a bigger role. This slide shows the main process for dry kiln production of cement. So we have the raw meal feeding in at the top, and this is a mix of a calcium carbonate source, usually limestone, with aluminosilicate source and other materials. So that's fed into this top of a series of cyclones where the raw meal undergoes drying and preheating before it moves to the calciner. And in the calciner, this is where the calcium carbonate is converted to calcium oxide with release of carbon dioxide. So I've got the numbers later, but a large share of the carbon dioxide release is inherent in the process. This is why carbon capture features strongly in decarbonisation roadmaps for cement. Now, the heat for these cyclones is coming from the kiln. So after the calciner, the calcined meal moves into the kiln, where it sees a gradually increasing temperature as it travels down the kiln and undergoes sintering to produce the final clinker. So traditionally, the heat in this kiln is provided by fossil fuels, and the thermal energy use in the manufacture of cement is about 38% of the total energy. So there's opportunities to substitute 38% of this total energy by biogenic fuels. And the feeding point where the biogenic fuels can come in is shown by the arrows. So there's firing in the calciner to bring this temperature up to required temperature, where fine and coarse solids can be added, as well as liquids and sludge. There's a secondary firing point which can take lump fuels to keep the temperature up in the kiln, and then there's the main firing in the kiln, which takes fine pulverized solids or liquid fuels. So the choice of biogenic fuel that could be added would depend on where it's being added in the manufacturing process. So this slide shows the decarbonisation pathway that's been published by the Global Cement and Concrete Association to reach net zero by 2050. If no reduction measures are implemented, then you can see that the CO2 emissions are projected to increase by 2050 because of increased production. And then there's various places where efficiency savings can be made. Obviously, efficiency savings means you're using less energy, so there's reduced carbon dioxide emissions. So we have efficiency in design and construction, efficiency in concrete production, savings in cements and binders, savings in clinker production. This is the process I just showed on the previous slide. So this is where biogenic fuels can come into play. We've got carbon capture, utilisation and storage as a big player as well in decarbonisation, and then there's decarbonisation of electricity and other processes to capture CO2, which are detailed in the report, not covered here. Now, actually, the use of alternative fuels to fossil fuels is commercial, and it's happening around the globe. And the graph on the left shows the global usage of alternative fuels that aren't necessarily biogenic. So we have refuse-derived fuels, including plastics, other fossil waste, mixed industrial waste, solvents, tires is an important fuel, and so on. And then on the right, we have the usage of biomass fuels and percent usage globally, where you can see sewage sludge is an important fuel, animal meat and bone meal, agricultural residues, even things like diaper waste, animal meat, animal meat and bone meal, and wood fuels as well. And the global average for alternative fuel use is just over 23%, but the EU is doing much better than this, and the EU average is 53% of thermal energy is from these alternative fuels or biomass fuels. So yeah, I said I had the numbers later. This is the inherent CO2 emissions from the calcining of the limestone, which is 55%. So this is why we need carbon capture and storage on that decarbonisation roadmap. For the alternative fuels, we want high biogenic content if we're going to be displacing fossil CO2 into the atmosphere. And some of the important ones are sewage sludge, refuse-derived fuels, animal meat and bone meal, agricultural waste, and wood waste. And as I've said, the EU average for the alternative fuels is 53%, but some plants in Europe are using much more than that. And some are aiming to displace 100% of their fossil fuel. So there's, for example, a case study in the report for Schwenk Manufacturing, a German company, where I think all their cement manufacturing processes sites are using more than 94% of alternative fuels. So highlight alternative fuels, including biomass waste, are commercial for cement manufacturing. There is potential to replace 100% fossil fuels for the process heat. And obviously it requires regional support mechanisms to make that happen around the globe. One thing I wanted to say was that it also depends on the waste management practices and how good the waste supply is, because obviously you need a secure source of alternative fuels. So moving to iron and steel manufacturing routes. This slide shows the main methods that are used globally for iron and steel production. On the left-hand side, we have the blast furnace route, where we're feeding coke and iron ore and sintered iron ore blended with coke breeze, which is the fines from the coke production, produces agglomerates, and they're also fed into the blast furnace. In the blast furnace, the iron ore is reduced to molten iron, and then that passes to the basic oxygen furnace, where residual carbon is decreased at high temperature combustion to produce molten steel. And then the other route is from the direct reduced iron route. So again, this takes iron ore and coal and other fuels, depending upon the technology, and it reduces the iron ore to iron without melting it. So it doesn't go through the liquid stage, and you get direct reduced iron from that. And that's usually fed into an electric arc furnace. And of course, you can also put scrap steel in the electric arc furnace as well. The blast furnace route is responsible for about 70% of global steel production, and the direct reduced iron responsible for about 25% of global production. The blast furnace route is the most carbon intensive route, and the most carbon intensive part of the process is the coke production and the blast furnace. So how do we go about decarbonising steel manufacturing? This slide comes again from the International Energy Agency's modelling of decarbonisation scenarios, and two scenarios are shown, gigatons of CO2 emitted per year as we progress through to 2050. The first scenario is the STEP scenario, which is the stated policy scenario, and this is the trajectory based on all the agreements that are currently in place with the Paris Agreement and all the rest. So because steel production is going to be increasing, even these stated policies won't result in a decrease in the carbon emissions from that sector. The other trajectory is the sustainable development scenario, and this scenario is more in keeping with the goal of reaching net zero of the whole energy system by 2050. So there's not a plan to decarbonise the sector to zero, but there's a plan to halve it more or less by 2050, halve the emissions. And we can see where energy savings are going to come from. Again, there's efficiency savings, technology, implementation of best available technology that will improve efficiency, reduce coke consumption. Electrification and hydrogen again feature strongly, and there's various processes being developed with injecting hydrogen into the blast furnace or direct reduced iron to offset some of the carbon that's currently used as a reductant. There is a role for bioenergy, and from this scenario, it's estimated globally to be around a 6% reduction by 2050. So what are our opportunities for biomass in those manufacturing routes? So on the top half of this figure, we've got the blast furnace basic oxygen furnace route, and on the bottom half, we've got the direct reduced iron route into the electric arc furnace, and then also shown is smelting reduction, which is only a small fraction of the steel manufacturing, so I'm not talking about that here. But the red boxes show the places where biomass could make some substitution, partial substitution for coal or coke material. So in the coking process itself, in the sintering process, in the carbon agglomerates that are added in the blast furnace, and also in the coal that's injected into the blast furnace. So these are some of the routes where biomass can come in. There's no carbon added in the basic oxygen furnace. And then in direct reduced iron, those processes that use coal, you can substitute for biomass, partial substitution. And actually there's carbon added in the electric arc furnace. So that is an opportunity for biogenic carbon substitution as well. So I just want to spend a little bit of time talking about a couple of those processes in a little bit more detail. So here's the blast furnace and some of the chemistry that goes on. The carbon that's introduced, one of the key carbons that's introduced is the coke. The blast furnace is a very tall, 100 meters more in height. Coke has a strong mechanical strength, and it's added in layers with the iron ore and the sintered material and coconut, which is slightly smaller size fractions of coke, and it creates a permanent permeable bed because our reductants are moving up through the bed and gradually reducing the iron ore as it travels down the blast furnace. So we add in our iron ore, sinter, fluxy materials at the top, coke that's added at the top. Eventually it will act as a reductant, but it's also acting as a permeable mechanical support, and it will also provide some thermal energy as well. So it needs specific properties if we're looking for substituting coke for biogenic sources. The other place that carbon comes in is in the injected two-air region at the bottom of the blast furnace with air or with oxygen-enriched air. And this is where pulverized coal comes in. And here, the requirements are a rapid reaction, rapid release of thermal energy. And as I said, traditionally that's pulverized coal, but this is a place where biomass and biomass-derived products can be added. The other process I want to look at is the electric arc furnace. And carbon actually provides a role in the electric arc furnace. So there is added carbon in the process. We have scrap material going into the electric arc furnace as well as direct reduced iron. This contains some carbon materials, some residues, oils, grease. There's carbon in the direct reduced iron as well. But sometimes carbon is also added in here. So coal and coke are added and other alternative fuels are added. And it provides a large fraction of the thermal energy needed to melt this iron down and start to remove carbon from it and form steel. The other place that the other place that carbon comes in is these oxy-fuel burners that also provide heat in the electric arc furnace. And then, of course, the rest of the energy for melting this mix comes from the electrodes, so it's electrical. So it's less carbon intensive than, it's not a highly carbon intensive process, but we are adding carbon into this system. And the injected carbon is important. It starts to form bubbles of CO2 and CO and so on as it burns, and that CO moves through the melted material and through the melted slag on top, and it starts to produce a foam within that slag. So the slag becomes a foam, and that protects the walls of the electric furnace and protects the electrodes as well. So a lot of the research on putting biomass in has been around this foaming behavior, and also obviously the chemistry that goes on in here to try and get the iron to the right level of carbon to produce steel. So blast furnace and basic oxygen furnace and direct reduced iron and electric arc furnace are the dominant technologies that are used globally. Both rely on coal and coke, and partial substitution from biomass in these different areas of the plant is being researched and is being implemented in some cases. So I just want to talk a little bit about the carbon science and charcoal versus coke. When you heat up biomass, it starts to decompose and it'll eventually form charcoal, shown on the left here, or sometimes referred to as biochar. The two are used interchangeably, but from my point of view, I think charcoal should be used when we're talking about woody biomass and biochars for other types of biomass. So we have our charcoal. Now, charcoal is actually has the carbon structure that's depicted to the right of that image of charcoal. Each of those little stacked layers, it represents a kind of graphite-like crystallite, a small region, nanometers in size, that's aligned planes that look a bit like graphite. But all these crystallites are randomly oriented, and they're in an amorphous carbon structure as well. So this is known as isotropic carbon. And isotropic carbons, because of this random orientation of the crystallites, it creates a very porous, microporous structure. It's great for activated carbons, high surface area. But this also means that charcoals have inherently high reactivity compared to coke, which I'll talk about in a moment, and low mechanical strength because of their structure. Coking coal passes through a fluid phase when it's heated very slowly, known as the mesophase. And because coal of this specific rank and maceral composition will have a certain amount of tar produced, it forms this mesophase that allows these crystallites to start to move and align before it solidifies into coke. So coke is actually an anisotropic carbon where you've got this general alignment of the crystallites, and this is characterized by low porosity, a low reactivity and a high mechanical strength. So in the blast furnace, where it's got to survive to the bottom of the blast furnace and provide a strength for the burden of material that's in the bed, it's a perfect material. So you can't have 100% drop-in fuel from charcoal to replace coke. There are a few smaller blast furnaces, for example, in Brazil, they're mini blast furnaces, and they have been demonstrated to run on just charcoal. But all the other big blast furnaces, they're not going to be able to have a drop-in fuel from charcoal for these reasons. And this just brings home what I was just saying. It shows the first two columns are the ones I want you to focus on. It compares coke lump with charcoal, a high quality charcoal. We've got this coke reactivity index, carbon reactivity index, CRI, which is the reactivity for carbon dioxide gasification. And for coke, we want this index to be less than about 23, and charcoal it's much higher. And the CSR is the coke strength after reaction. So as the carbon strength after reaction. So as the material gasifies with CO2, it opens up the structure. It makes the strength decrease. But you can see that for coke, it has a high value. For charcoal, it's a lot lower, and the compressive strength is a lot lower, and so on. So charcoal cannot be a direct substitute for coke. And actually, most of the research in that area is, sorry, I'm getting ahead of myself. Most of the research in that area is around how much biomass you could substitute into coke making and still have acceptable quality coke. So CARMs can be anisotropic coke or isotropic charcoal, depending on the precursor, and the inherent porosity and reactivity of charcoal and biochar affects how they can be used in iron and steel manufacturing and how much could be used. So just a brief summary of some of the RD&D. I'm not covering everything. There's a lot more detail in the report. As I've said, there has been a lot of work on substituting biomass into coke production or charcoal into coke production. It's been widely researched for maybe 10 to 15 years, maybe a bit more. And loads of different biomass materials have been studied in different blends, different types of coal. And the consensus is really that because of this different structure that biomass has, it actually affects the fluid phase that the coke goes through as it's heated. So it decreases that fluidity, and the resultant coke that's produced has a lower strength and a higher reactivity. So looking at the research that's out there, it looks like 2 to 10% substitution of some of the coal with biomass might be feasible. It's very dependent on your blend of coals that you're using and the biomass that's being used. But that can deliver coke with still acceptable properties. It is an ongoing research area. There's a lot of research going on in trying to understand at a very fundamental level what's going on and whether you can optimize the blending to allow you to have higher substitution of different biomass types. Another area that has had a lot of research and development is actually at one of the highest technology readiness levels is injection of biomass or charcoal into the blast furnace, at the base of the blast furnace. And here you want a small particle size, it's pulverized, and you want rapid reaction to release the heat quickly. And actually pre-treated fuels, thermally pre-treated fuels like torrefied fuels, charcoals, they have more attractive calorific value and grindability than biomass itself. So there's a lot of interest here in using torrefied materials, biochars, and other types of pre-treated biomass, hydrothermal carbonisation, and so on. The conveying and injection of those thermally treated biomass at a high rate is still a challenge, and also, of course, those types of fuels are more reactive, and so the dust explosivity needs to be considered from a safety point of view, and suppression equipment installed and all the rest. But there is very good potential, especially for charcoal. The research has shown that it gives more complete burnout than some of the coals that are used, which means that it's higher efficiency. So it lowers the coke consumption. There's less coke being used to provide thermal energy because you've got good reaction of the charcoal in the hottest parts of the blast furnace. And actually high technology readiness level has been achieved, and I've got a case study to show that in a moment. So in theory, high substitution rates are possible, but actually in practice, it's limited by these points of how much you can actually convey and inject at a high rate that's needed. The other place that biomass is being used is in the electric arc furnace. There's been a lot of studies in this area, and actually at quite larger scale, because it's a batch process. It's easier to study in that system. It's smaller scale than a blast furnace. It's a batch process, so it's easier to undertake trials. And the biomass has been added either as charged carbon or as injected carbon. And most of the focus for the injected carbon, as I was saying earlier, is understanding how the substitution of coal for biomass products affects this slag foaming behavior, which isn't fully understood. And also, there's also been a lot of laboratory work and scaling that up to how it will actually implement on a large scale isn't fully understood. So probably injected carbon is at a slightly lower technology readiness level than the charged carbon. And for the charged carbon, it looks like it's probably ready for implementation. As long as the ash is low enough in the charged carbons. Waste sand residues are of interest, and actually there's alternative fuels being used as well in the electric arc furnace, like tyres and so on. But I think there's been demonstrations of substituting a third of the anthracite that's added by biomass briquettes. And there's interest in the most attractive material seems to be woody biomass and nutshells, and making briquettes and so on of those. So that's at slightly higher TRL. Having a secure and available supply is an important factor in considering implementing this technology, and economic incentives. Depending upon the material, it's probably going to be more expensive than the coal it's displacing. So what we've tried to capture here is what the technology readiness level is for adding biomass and biomass products in different processes in iron and steel manufacturing, with the percent biomass addition at the bottom. And if I were to add cement onto here, we would be at the highest TRL and up to greater than 95% biomass addition. Is, well, certainly greater than 90% is already being done. So just to point out some of the things I've said, the charcoal addition in the blast furnace, in the mini blast furnaces, has been done at scale, and has displaced 100% coke in a few plants in Brazil. It's been demonstrated there. and also charcoal injected into the base of the blast furnaces. And then on the bottom left, we have processes that are limited in how much biomass they can take. So things like blending biomass in coke making, and it's at a lower TRL. And in the middle, we have the adding biomass into the electric arc furnace, replacing nut coke, which is a smaller sized fraction of coke in the blast furnace, by charcoal, has also been trialled. And then torrefied biomass injection into the blast furnace, which I'll show in a moment. So thermally pretreated biomass and charcoal are able to substitute for coal and coke, but at varying levels in different operations of the iron and steel plant. And a lot of the research is around what the maximum substitution rates are. So just to show one case study, there's it's from the report. This is a demonstration that's being built by ArcelorMittal, who are in the top 3, they might be top 2 global steel producers. They produce 59 megatons of steel in 2022, and they operate all around the globe. And they are constructing an industrial scale torrefaction plant, which will take waste wood and convert it into what they call biocoal. And it's using Perpetual Next's technology. They acquired the Tor coal technology, and it's actually this Tor coal technology. And the plant investment is 35 million euro. Funding has been from Horizon 2020, the European Investment Bank, and the Flemish government. And it'll take 88,000 tonnes of waste wood per year, convert it to 37,500 tonnes of biocoal per year. The biocoal will be injected with pulverised coal into their blast furnace at this site in Ghent, I believe, in Belgium. And the displacement of the fossil CO2 from that process is estimated at 112.5 kilotons per year. In an added innovation, they've also got on that site a process they've called the steel-anol process. And this uses 4 biomass reactors and technology from LanzaTech, which is a biological conversion process. It takes the off gases, carbon-rich off gases from the blast furnace process and ferments that to produce bioethanol. Well, to produce ethanol, I should say. Obviously, if some of that CO2 is now from biomass products, then you've got a bio element in that ethanol. And once all 4 of their reactors are fully operational for that steel-anol process, that is estimated to be using 125,000 tonnes per year of CO2. So it's a nice example of a kind of circular process for displacing coal, capturing carbon, utilising carbon. So just some final comments. A really important one, of course, whenever we talk about bioenergy is the supply chain. There's always issues, potential issues of land use change, so starting to grow, changing a land from one use to another has a carbon payback period associated with it. Being careful that pressure isn't, that natural forests aren't under pressure, and so we don't have deforestation or loss of biodiversity. Depending on the biomass, there might be water use and fertilizer use issues. There's always consideration of the supply chain itself and emissions during cultivation, collection, densification, transportation. So for any bioenergy project, these are important considerations. An added one for charcoal production is the vast array of sophistication of kilns around the world. A lot of the charcoal use in Europe is coming from Africa, and some of those kilns are very basic. So some of the kilns that produce charcoal in Africa are very basic, I should say. Of course, there are good technologies for charcoal production, industrialized processes that recirculate the gases from and vapors from charcoal production back in and increase the yield of charcoal and produce higher quality charcoal. But some of the kilns that are out there are very low efficiency, very polluting. And so that is another factor that really needs to be addressed if we're looking at substituting charcoal into the blast furnace, for example. Of course, the torrefaction plants tend to be a lot more sophisticated. They are commercial processes on a large scale, and many use best available technology. So there are technologies out there that can produce the material that's needed at scale. Just we need to be careful that these are implemented. And so the life cycle analysis for this whole supply chain is really critical, not just in ensuring that all the right boxes are ticked, but also ensuring that we are achieving carbon reduction benefits in the process. We need to ensure positive social impacts as well as environmental impacts and good employment practices while delivering a secure and affordable supply. So for operators, balancing all those factors and still making it economic is a key challenge. So the last discussion really is around policy measures to make the decarbonisation roadmaps happen. Early retrofitting of all these carbon reduction measures is really important for having the largest benefit for limiting global warming. So we need to accelerate really the implementation of these decarbonisation options so that we have the greatest benefit. And bioenergy is just one of a suite of options for decarbonising heavy industry. And as I've said, regulation, certification, inspection of supply chain is really critical. And to date, the transition has been slow. As I've said, both sectors aren't on track. Policy efforts in some parts of the world are still in the early stages. But some of the enablers include direct research and development funds. For example, the European Union, Europe has the Clean Steel Partnership, Japan has a Green Innovation Fund, and these are helping to develop new innovations. There's market-based incentives. The carbon price promotes a reduction in emissions. The border adjustment tariff helps reduce carbon leakage and stimulate investment in greener technology. So what it tries to do is put a tax on lower value products that are being imported, say from a part of the world that has a high carbon intensity into a part of the world that has a lower one. There's also things like public procurement commitment to green steel to start to create a more viable market for that production pathway, and of course capital grants. There's a $2 billion EU of public funding for hydrogen DRI, the direct reduced iron development, for example, and there's other grants for CCS on cement production in Europe. Another thing that's really important is those technology roadmaps have roles for carbon capture and renewable hydrogen and electrification. So really the infrastructure development to support that needs to go in hand with the implementation of technology innovation so we can get the earliest deployment and the greatest benefits. There's also significant co-benefits by doing this. Obviously, there's the climate issue, but there's all sorts of other sustainable development goals that would be ticked by implementing these. And the other point to make is that because a lot of these decarbonisation options are efficiency savings, they're also financial savings. So some of them are, are going to deliver good economic impact as well as good climate impact. So perhaps that understanding that is important to attract the necessary investment and put the necessary policies in place to make it happen. So bioenergy is going to play a modest role in decarbonising iron and steel, slightly larger role in cement, well, a much larger role in cement, and injection of carbonised biomass at the highest TRL. Economics versus sustainability credentials is of course a core issue, and many decarbonisation options deliver energy and financial savings as well as environmental and social benefits. So the sooner we can implement these, the bigger the advantage. And that's the end. Thank you for listening. I will have a look at questions. I'm not seeing any questions. I don't know if the organisers are there. I can't see any questions, so.
No, we usually just give them a couple of minutes to come in.
Okay, okay.
Great webinar, Jenny.
Thank you.
And we have a few of we have Bijal and Delani also on the panel for your questions in case.
Perhaps I took a bit too long and people had to leave. Or I've answered all the questions. We could put a positive spin on it.
Absolutely. And plus, there's also your email address in case anyone wants to send.
Yes, of course. Yeah. Yeah.
I think I see a question here. So from Brazil, do you know any projects in iron or cement in Brazil?
Sorry, what's the question? I can't see it for some reason. Oh, hang on. No, I can't see the question.
Do you know any projects of INS or cement in Brazil?
Yes. Yes. So in Brazil, they've got a long history of using charcoal in the blast furnace plant and in the integrated plant and also in their pig iron production. But they still use a lot of coal. I think the numbers are something like for 2021, this was, I've got it here, 57% coal, 18% charcoal and 10% electricity. So charcoal use average charcoal use has been higher than that, but it's been decreasing over recent years. I think there were, I'm trying to remember now, I think there were 11 iron and steel plants that were converted to take charcoal in their blast furnaces, and I think 3 of those were able to run on 100% charcoal. But what I don't know is whether they're still running at that level. There's examples of some good examples of projects in Brazil where eucalyptus plantations have been established that have sort of forest certification for sustainable forests and forest stewardship certification and so on. So Aparam have a biochar division, Aparam Bioenergia, that look after those, that manage that forest, and that is then used to produce charcoal in industrial kilns. So good efficiency in the kilns and so on, and then that charcoal is transported to their plant, the Timoteo plant. So that's one example. There's a couple more examples in the report.
Great. And yeah, there's another one here. For cement, does the use of bio have any impact to the product, cement?
Oh, I can see it now. I can see the question.
Great.
Oh, can I, Lilani, do you have time to address, can you address that one?
Yes, it does, because when they introduce the fuel, the gases that come from the fuel and the ash, everything is in contact with the product. In fact, the ashes from the biomass combustion is incorporated into the clinker matrix. So it does, oh, sorry about that.
Yeah.
Go
So
ahead.
yeah, the ash is incorporated into the clinker, so it impacts the composition of the cement. So it does mean that needs to be managed, and selection needs, the selection of the fuels that are used needs to be considered. But in some instances, I think it means you can decrease the amount of other materials that are being added as well. So there's some co-benefits. Lilani's written the main chapter on that, so she is our expert. I don't know if she's back.
I am back, Jenny. Sorry about that. So, but the selection of the fuels that are going to be injected, and the point of injection is important. Pre-processing of the fuels as well, to make sure that they meet the characteristics needed, especially in terms of minerals. For example, chlorine is one of the main ones that is limited. Although there are ways to deal with that, with bypasses, etc., at the plant. Silica, for example, is another one. But the requirements for the cement have to be met. There are standards for the different types of cements, and there are cements that can accept more biomass ash than others, depending on what their use is going to be. For example, cements that require quite a lot of strength, for example, that are going to be used in areas that are prone to earthquakes, like Japan, for example, where we will probably not take much of that biomass ash as some others.
I can't see. I'm really sorry. For some reason, the question box isn't working as it should. So, Benedicte, if there are other questions.
Yes, there's one here. Where would all the wood come from to displace coke and coal? Burning wood is not carbon neutral.
Yeah, and okay, this is where the life cycle analysis becomes important. No, it's not going to be suitable for every part of the world. There are models out there that have looked at matching where biogenic sources are to where the heavy industrial sites are. I think for certainly using wood to displace coal is not without controversy. And so the management of that supply chain and ensuring the carbon savings are happening and the sustainability is happening is always a key. But you can achieve carbon reductions by displacing fossil fuel with wood products, as long as you look at the whole life cycle and the sustainability of that. For cement manufacturing, of course, some of the fuels that are used are waste fuels, so there's less controversy around those. And some of the plants that, the example I showed, the case study, it's actually taking waste wood for the iron and steel process as well. So yes, I agree, it's not going to be for every plant, and this is why it's only contributing a small percent to the decarbonisation roadmaps. But there are parts of the world where it would make sense to do that, and there's some plants where it would make sense to do that.
Great. There's another one here. The use of RDF in cement production has become quite popular in Europe, but less so elsewhere. RDF can also contain biomass components depending on source. Has the amount of biomass in RDF been considered in any other data you presented?
I think it has. I think whenever getting the numbers right from the Global Cement and Concrete Association, when they compile their data, they do take into account the biogenic fractions of the different types of alternative fuels that they use, so they can account for it as a biomass fuel, as a percentage of biomass fuel. As you've seen from the slides, the European cement industry tends to use a lot of waste materials, some of them which are biogenic in origin, and many of them which are mixed, including rubber tires, for example, which has a proportion of biogenic material rubber, and they do make that distinction.
Great. There's another one here from Indonesia, I believe. As we have known, the issue related biomass supply is transportation. How's the iron and steel industry going to deal with this issue?
Yeah, I think this is related to the previous question, and it's about understanding plant-based solutions for, for your particular iron and steel plant. I think there's a lot of tools now that can be implemented to assess supply chains and what's going to make sense. And I agree, it's not just cost for transportation, it's part of the life cycle emissions that have to be considered. So I think some of these models that are starting to be developed that can use things like GIS mapping to look at what's within a certain accessible area for your plant, or looking at waste resources if that's relevant. So that you can start to look at what feasible biomass use there is, what the options are, what's feasible, what's going to give the biggest carbon savings. And there is research out there that has looked at modeling these. There's even plant by plant analysis, a big paper that was published last year in Nature, that did a plant by plant analysis on where biomass might come in. So yeah, of course it has to be considered, and it's not a sweeping solution to the whole sector. It's in some plant it might be more significant than in other plant, depending upon where it is in the world.
Great. I think there's one more. Another issue in biomass is high volatile meter. How do you ensure the energy is produced, as there's a possibility to burn before it goes to the boiler?
Yeah. I guess this question is around the fact that if you're using charcoal, you've already lost the volatile matter. I think this is what the question is about. But this is why, or if you're using torrefied material, but usually that volatile matter is incorporated in the manufacturing of the solid material. So you are using the energy in those volatiles for the production of the charcoal or the production of the torrefied material. So they have already been used. They're not, and if you've got a good manufacturing process for your thermally treated solid, then you've already used those, and that's best practice to do that.
Can I just add, Jenny, to that, that cement, that's why when you show that slide with the different injection points, they all have different particle sizes, don't they? And that is to ensure stability of the system and to ensure complete burnout of the particles. But there is a possibility with high biomass chairs of affecting the stability because of this volatile matter, as mentioned. And that's when they have been proposed to use gasifiers, for example, in pre-combustion burners to pre-treat the fuel, to pre-burn the fuel prior to introducing into the calciner, for example. But these are not as widely used, I think.
Great. I think this might be the last one we have time for. If existing cement plant incorporate bio into their process, does that affect emission in any way, the flue gas?
Do you want to take that?
It does have an impact. The fuel does have an impact on emissions, but overall they have been seen a reduction in NOx because of the lower nitrogen content of biomass in general, and also in sulfur oxides.
Yeah, the other thing that about the kiln is that because the conditions in the kiln, it's amenable. The conditions prevent or minimize the route to dioxin furan formation. So if you are using fuels that might, be susceptible to producing those, the kiln minimizes their production. The conditions in the kiln, the long residence time, the high temperature.
I mean, the kilns are considered better. Sorry, Jen.
No, carry on.
I was going to say that the kilns are considered to have better combustion conditions, or present better combustion conditions than incinerators even.
Yeah.
They are considered more efficient and in producing energy and combustion.
Yeah. I should say that in the report we haven't covered much on emissions because we had to keep it fairly focused. There wasn't enough space to go into detail on the impact on emissions. We just mention it where it's relevant. So yeah, if you're hoping for more on that in the report, there isn't much more.
Okay, but I think we'll wrap it here. Thank you so much, Jenny and Bijal and Leilani. Thank you so much for joining at the bit here. End
Okay,
bit.
thank you.
Okay.
Okay.
And all that's left for me to say is the slides from this webinar will be available to download from our webinar page shortly. And thank you all for joining us today, and goodbye.
Thank you. Bye.